The number 400 watt-hour per kilogram has hovered over the battery industry like a technological holy grail. But what does it actually mean? And why has it become such an obsession? Electric vehicles could realistically travel 600 miles on a single charge. Humanoid robots and industrial automation systems could operate for entire shifts without needing to recharge. So if the payoff is so enormous, why do we keep hearing about 400 watt-hours per kilogram in press releases and lab papers, yet never see it in showrooms or charging stations? Let's deep dive into this episode today and become our first subscribers for the channel. Thank you, fellas. Why does higher energy density almost automatically mean lower stability? At the atomic level, storing more energy means forcing electrodes to operate closer to their chemical and electrochemical limits. Bonds that are comfortable and stable at lower energy densities become strained when we demand more electrons per unit mass. In practical terms, this is why lithium-metal anodes and high-nickel cathodes look so attractive on paper yet behave so badly in real cells. Consider lithium dendrites, the needle-like metal structures that form when lithium plates unevenly during charging, at moderate current densities. Modern graphite anodes manage this risk reasonably well, but at energy densities approaching 400 watt-hour per kilogram, lithium metal becomes almost unavoidable, because graphite simply cannot store enough lithium per gram. Lithium metal has a theoretical capacity of 3,860 mAh, nearly 10 times that of graphite. Sounds perfect, right? The problem is that lithium metal is chemically aggressive and mechanically unstable. During repeated charge and discharge, dendrites can grow through the separator and short-circuit the cell. One internal short in a battery storing 400 watt-hour per kilogram is not a minor defect. It is a trigger for catastrophic failure. Volume change makes this even worse. Silicon, another favorite candidate for high-energy anodes, expands by up to 300% when fully lithiated. In laboratory coin cells, clever binders and nanostructuring can partially tame this expansion, but in real automotive-sized cells, repeated swelling and contraction pulverize the electrode structure from the inside. Cracks form, electrical contact is lost, and fresh surfaces are exposed to the electrolyte, accelerating unwanted side reactions. The cruel irony is that the very materials we need to reach 400 watt-hour per kilogram are the ones that mechanically destroy themselves the fastest. If material instability were the only problem, engineers might brute force their way through it with clever designs. But the second challenge is even less forgiving: thermodynamics and safety. What actually happens when something goes wrong in a 400 watt-hour per kilogram battery? Today's lithium-ion cells already contain enough energy to cause serious fires, yet their thermal runaway is at least somewhat manageable with cooling systems, separators, and flame-retardant electrolytes. At 400 watt-hour per kilogram, the situation changes dramatically. Thermal runaway is a chain reaction. A small local defect causes heat. Heat accelerates chemical reactions. Those reactions release more heat. In current EV cells, the heat release rate might reach several hundred watts per cell during failure. At 400 watt-hour per kilogram, simulations and small-scale experiments suggest that energy release could be 1.5 to 2 times higher for the same cell size. That means faster temperature rise, less time for safety systems to react, and a much higher likelihood that one failing cell ignites its neighbors. From an engineering perspective, this forces designers to add thicker casings, stronger separators, and more aggressive cooling pathways. Here is the uncomfortable question no one likes to ask in marketing presentations: how much dead weight do we need to add to keep a 400 watt-hour per kilogram cell safe? Pressure is another hidden enemy. High-energy cells often generate more gas from side reactions, increasing internal pressure over time. To prevent swelling or rupture, the cell housing must be stronger. Stronger housings mean heavier housings, and heavier housings push the practical, pack-level energy density back down. Many prototypes proudly report 400 watt-hour per kilogram at the material or laboratory cell level, but when packaged into a safe, road-legal battery pack, the number quietly drops to 280 or 300 watt-hour per kilogram. Physics has a way of collecting its debt. Even if we momentarily ignore safety, a third challenge looms: large cycle life. Is a battery really useful if it hits 400 watt-hour per kilogram but only survives a few dozen charge cycles? This is where the trade-off becomes brutally clear. You can design a cell that delivers astonishing energy density for the first 10 or 20 cycles. Military or experimental aerospace applications sometimes do exactly this, but consumer electric vehicles demand endurance. A typical EV battery is expected to retain at least 80% of its capacity after 1000 full cycles, which corresponds to 300,000 miles of driving. At higher energy densities, degradation mechanisms accelerate. High-voltage cathodes, often operating above 4.4 volts, aggressively oxidize the electrolyte. This leads to thicker and less stable interface layers, consuming active lithium with every cycle. On the anode side, unstable solid electrolyte interfaces continuously break and reform due to volume changes, again consuming lithium and reducing capacity. Experimental data shows that while a 250 watt-hour per kilogram cell might lose 10–15% capacity after 1000 cycles, early 350–400 watt-hour per kilogram prototypes can lose the same amount in fewer than 200 cycles. That might be acceptable for a drone or a missile, but it is unacceptable for a family car. So where does that leave the industry? Are there real solutions? Or is 400 watt-hour per kilogram just a fantasy number? Solid-state batteries are often presented as the silver bullet by replacing flammable liquid electrolytes with solid ones. The hope is to suppress dendrite growth and eliminate thermal runaway. On the anode side, unstable solid electrolyte interfaces continuously break. In practice, solid-state batteries introduce new problems: high interfacial resistance, brittle materials, and manufacturing challenges at scale. Many solid electrolytes also require high stack pressure to maintain contact, once again adding structural mass that eats into energy density. Lithium-metal anodes remain essential if 400 watt-hour per kilogram is ever to be achieved. The challenge is controlling lithium deposition uniformly over thousands of cycles. Researchers are experimenting with artificial interfaces, 3D current collectors, and electrolyte additives that promote smooth plating. Progress is real but incremental. No solution yet combines high energy density, long cycle life, and low cost in a single and manufacturable package. Nanotechnology offers another partial answer. By designing electrodes with nanoscale features, engineers can accommodate volume changes and shorten diffusion paths for ions. This can improve power capability and reduce mechanical stress. However, nanostructures increase surface area, which often worsens side reactions with the electrolyte. They are also expensive to manufacture at the scale required for millions of vehicles per year. So, what did you think about this? Subscribe to our channel and leave your ideas in the comments. Thank you, fellas.